is your formal introduction into the course, right? Really, why are we thinking about using data science techniques in material science, okay? So this, you can treat this like basically your overview introductory to this topic. All right, so let me first define what data science is. So data science is a multidisciplinary field that uses scientific methods, processes, and algorithms and systems to extract knowledge and insights from structured and unstructured data, okay? So this is basically the key part that I want you to focus on. Essentially what we are trying to do when we apply data science techniques to materials data is to extract insights and knowledge from that data, right? So things which will allow us to either understand what is happening with a material, and hopefully also how do we go about improving that material or discovering new materials that can have better properties, okay? So when we think about data science, we usually think of it as an intersection between multiple domains. So there is, of course, your domain knowledge, which in our case would be the material science knowledge, things that you yourself has learned as a material scientist, right? So what are the rules of chemistry? What is the periodic table? What is the crystal structure, for example? It intersects with the field of computer science. So essentially, how do you apply machines and algorithms to analyze data and to actually process them, okay? So when we actually combine our domain knowledge with computer science, we are essentially doing data processing. And finally, we have the field of mathematics. Essentially, these are the algorithms and models which enables our machines to learn from the data and try to develop new predictive capabilities, okay? So when we combine mathematics with computer science, this is basically where your machine learning sits, and the combination of the three essentially is where your data science sits, okay? Now, this is probably a plot that you guys have seen somewhere in some form, and maybe you are not aware of an age where we don't have that much data. I was born slightly before the internet age, okay? So I lived through an age where we had modems, okay? And essentially the world has gotten to a stage where we are generating data at an exponential rate, okay? So you can see that back in 2005, the world as a whole is generating about 0.1 zettabytes of data. By 2020, we are really talking about 47 zettabytes, and we project that by 2025, that number is going to balloon to 163 zettabytes, okay? So in order for us to make sense of all this data, we need to use new techniques, okay? And this is not just true of data in general, but also of materials data, right? Now, in the past decade or two, we actually have begun to really get into a stage where we are generating materials data at a rate which now makes it possible for us to use some of these tools that have been brewing around in other domains to material science, to the field of material science, okay? So these are just some examples of data sources that are out there. So for example, the inorganic crystal structure database. This is a database that many of you may have used before, where essentially whenever someone discovers a new crystal structure of a material, they will submit those crystal structures to the inorganic crystal structure database, and they will actually compile all of them, right? And today, the ICSD has about, I would say, about 200,000 unique structures, right? So of course, in terms of entries, you have a few million entries, but we filtered it down to basically about 200,000 unique crystal structures, okay? You also have data such as the protein data bank. That is actually by much larger, okay? I apologize for the size of the font, but essentially it has about 1.8 million protein structures in that database today. and the growth rate is at about 10% per year. Okay, so again, that data resource is so growing rapidly, right? And there are other databases such as the Cambridge structured open crystallographic open database, as well as the Cambridge structured database, and you can clearly see that exponential growth in data in all these different data sources. Okay. Now, the problem with data in material science, though, is that even though our data is actually growing fairly rapidly, we are still lagging behind many areas in terms of both quantity and quality, right? So I'd like to use this example. So there's this very famous handbook that a lot of material scientists use. It's called the Handbook of Condensed Matter and Materials Data. Sounds impressive, right? So it is one of the most comprehensive handbooks of materials data you have out there. This is experimental data, right? So in this handbook, you can find things like the density of materials, the thermal and electric conductivity, the melting and boiling points, and so on and so forth. But if you actually go into the handbook, you will find that all this data is available for maybe a few hundred materials. Okay, most of them binaries, maybe a few ternaries, and not that many complex materials. Okay, so quite clearly, this is a very small. In the context of the present world, this is actually not a very big data set to work with. Okay, so it is not like, for example, if you want to analyze the retweets of an article, you easily can get numbers in the millions or billions. Okay. Now, this is another example. So this is a superconductor database. Okay, so a superconductor essentially is a material that below a certain temperature would have zero resistivity. Okay, and someone in Japan has decided to create this database called SuperCon, and it has about more than 1,000 superconductors that has been reported with information like their transition temperature and various other information. Okay, now this again it sounds reasonably impressive, right? Like you have at least a few thousand data points, but if you actually go into the database, you will find that most of the compositions are actually just very small modifications of each other, right? So maybe this compound has slightly more copper or less copper than the other neighboring compound. Okay, so in other words, the data is not very diverse in terms of chemistry. So this is always going to be one of the major challenges that you will face when you apply data science techniques in material science. Okay, it's always about, well, do I have enough data to do the analysis that I want to do, and whether my data is representative enough of the chemical or structural space I want to cover. Okay, so if your data is not diverse or big enough, you cannot actually apply a lot of the data science techniques. Now, one of the things that gives us optimism that that we can go about solving this data crunch issue is that before all this whole data science stuff came about, we already have methods in which we can generate data computationally. Okay, so previously materials data is generated very painstakingly, right? So for example, if I want to measure the thermal conductivity or electrical conductivity of a material, some material scientist has to go into the lab, they have to make that material, they have to measure it, and they have to do it very carefully in such a way that the experiment is well controlled, the composition is well controlled, and all those are very difficult to control. Okay, so and this is actually obviously a limiting factor, right? No matter how fast you do this, humans are always a limiting factor if you rely on humans to basically generate data. Okay, now, but since I would say about 10 years or even 15 years ago, we now have a way in which we can generate data and accurate data for a large number of materials very rapidly. Okay, and the method that I'm going to talk about is basically what is called first principles materials computation. Now, the way that first principles materials computation work is that you start from the basic equations of physics. So, for example, you're showing the equation, which applies to everything, okay? You can use it for any chemistry. You can then use some approximation to solve the showing the equation. You can then plug that equation into a computer, and by using that computer, you can essentially solve that equation for any collection of atoms that you want to simulate. Okay? Now, because we are using computers to solve the equations of physics, the good news is that computers are inherently scalable. Okay? So many of you have heard about Moore's law, right? So every 18 months or so, our computing power doubles, right? So when our computing power doubles, we can compute more materials, or we can compute more properties of the same material, right? So with the combined growth of computing power together with the fact that a lot of these software codes to solve the Schrödinger equation are rapidly maturing, we today now have the capability to generate a very large quantity of materials data just using computers without any human intervention. Okay? So this is just a sampling of some of the properties of materials that you can actually get out of first principle computations. So for example, you can predict things like the phase stability of a material. You can calculate diffusion barriers. This is actually very, very important in a lot of applications. So for example, I work in lithium-ion batteries. One of the things that I am interested in is how fast does lithium move through a material. Okay? The faster lithium can move through a material, the more likely it is to be a good lithium-ion battery cathode or electrolyte material, right? And calculating the diffusion barriers is one of the ways in which I find out how good a material is, okay? You can calculate things like the surface energies and Wolf shapes. Again, if you are working in catalysis, this is going to be a very, very important thing that you will want to look at. We can even calculate things like mechanical properties, okay? Things like what is the bulk modulus of a material, what are the full elastic tensors, and all these you can do using just first principle computations alone. And of course, one of the main outputs from a first principle computations is the electronic structure. So things like what is the band gap of a material, what is the effective mass, what is the DOS and band structure, and again, depending on what kind of materials you are working with, very, very important, right? If you are designing a solar cell, you would definitely want to know what the band gap of the material is, because you want the band gap to be at a range which will capture visible light and convert that to electricity, okay? Now, electronic structure calculations, like the one that I just talked about, has gotten very, very reliable and accurate, okay? What this means is that the software implementations have gotten so good that they are essentially consistent across different implementations, okay? So there's actually this science paper that was done back in, I would say 3-4 years ago, which compared all the different electronic structure software codes and whether they are giving you different answers, and the anticlimactic answer to that question is that no, okay? Every single software code seems to be giving the same answer, right? So within the limitations of the approximations that you use to solve the Schrödinger equation, the software codes are working as they should. They give you consistent answers, okay? And you can actually demonstrate that a lot of the predicted properties are at least in a qualitative sense correct, and in some cases quantitatively correct, okay? So how do I know this, right? So this is, I'd like to show you this example. So this is a plot of what we call the energy above the ground state for all the materials in the inorganic crystal structure database. So if you recall, as I said, the inorganic crystal structure database is this huge database of known materials that people have submitted into the database, right? Someone synthesized something, they did an XRD on it, and they say, well, this is the crystal structure, I'm going to send it to ICSD, right? So it is a sort of a proxy indicator that something is synthesizable, right? You can actually make it, right? And what you will notice is that if I plot the energy above the ground state for all the crystal structure in the inorganic crystal structure database, more than 80% of them fall within 100 MeV of the ground state, right? So this is a cumulative plot, and you'll see that at this 80% line, most of the materials actually fall within that 100 MeV per atom range, okay? In other words, today we actually have the ability, before someone go ahead and synthesize something in the lab, to actually do a calculation and say, well, this material is likely to be synthesizable or it is not likely to be synthesizable, okay? So we can actually give that experimentally at least some confidence, right? We can conclusively sometimes say that this material is not likely to be made. You probably can't make this in the lab, okay? This is actually a plot of the surface energies, and again, you can see that what on the x-axis is the experimental surface energy, on the y-axis is the calculated one. You can essentially see that they essentially lie on the one-to-one line. So again, fairly accurate, right? This plot shows the same thing for the bulk modulus, and essentially what we can show is that the predicted bulk modulus from first principle computations today is usually within 15% of the actual experimental bulk modulus, okay? Now, that is actually reasonably good, right? A lot of times, actually, when the experiments measure a bulk modulus, it is unclear whether they are measuring the actual bulk modulus of the material that we are talking about, okay? Because in experiments, there's always things like impurities and grain boundaries and that sort of things, which can actually affect the measurement, while in computations, it is always the intrinsic property of the material that you are trying to simulate, okay? All right. So there are software frameworks for high throughput computation material science. I'm responsible for building that whole chunk of the materials project infrastructure together with my colleagues in the materials project. So I already talked about PyMatGen. I'm not going to go through it again. There's this software framework called Custodian, which actually does error correction for calculations. And there's this Fireworks package, which does scientific workflows, okay? So in other words, sometimes when you want to actually calculate a property of a material, it's not a single step calculation, but rather you actually have to do 3 or 4 different steps of calculation. That's where Fireworks comes in. We have competitors, of course, okay? So things like the atomic simulation environment is another package out of Denmark that actually it was developed before our packages came about. So they does some of the same things, not completely the same. There's this thing called AFlow, and there's this relatively new package called AIDA, which also does some of the things that the materials project software infrastructure does, okay? Now, once you actually have computation and you have the ability to automate computations, essentially what happens is that people start generating very, very large databases of materials, okay? So these are some examples of the databases of materials out there. So there's one called the Open Quantum Materials Database, which is out of Northwestern University. AFlow is out of Duke University. The materials project is in Lawrence Berkeley National Lab. This is the project that I am closely associated with. And there's this thing in Europe called the Nomad repository, which is a much larger database of just the raw outputs of a calculation, okay? So all these databases, the commonality is that they have fairly large quantities of data. In other words, they usually have at least a few 100,000 data points, if not millions of data points. But there are differences in coverage, okay? So for example, in terms of things like hypothetical alloys, the AFlow database is probably more complete than the materials project database, while if you are looking for things like ceramics and you are trying to look for different properties of ceramics, the materials project database is probably much more comprehensive in that regard, okay? So in this particular course, we are going to basically just focus on the materials project, but in your very first lab, you will actually get the chance to compare the materials in the materials project with the materials that you actually get from OQMD and do some data analysis to cross-check the data, okay? So this is part and parcel of your very first lab, which you will get to do in the first 2 weeks.
Are they free to use?
All these databases are free. There are, of course, some private databases. So like, for example, ICSD is actually run by a company. You have to pay to use it. But as a UCSD student, you get free access to it. Okay? Any other questions? All right. If not, I'm going to talk a little bit about the materials project. So we already went to the materials project website just now. It is basically www.materialsproject.org. It is an open science project to make the computed properties of all known inorganic materials publicly available to researchers like yourselves to accelerate materials innovation. So this project was actually started in 2011, 2012 as part of what is called the Materials Genome Initiative. This was started under former President Obama. And essentially the MGI, or Materials Genome Initiative, is the aim is to fund computational tools, software, and new methods for things like materials characterization and computation to accelerate the discovery and development of advanced materials. Okay, so the way that the materials project people would pitch to you what the materials project is that you think of it like a Google for materials. Essentially, if you are interested in a property for a material, materials project really should be one of your first stops. You go there and you type in the materials formula, and hopefully, if you're lucky, that we have done a computation on it, and you can look up the property there. Okay, so today we have around the number has slightly increased, about 140 something thousand inorganic compounds. And if you go into the materials project website, just now I already showed you, you can call up the what we call the details page of any material, and that details page will contain things like the relaxed crystal structures, the band gap, the densities, volumes, and various other properties of the material. Okay. I already talked about the API, so I'm going to skip. But basically, the materials project API is essentially a way in which you can access materials project data in a very scalable approach. So rather than you having to go do an individual search and pluck out that data point, which obviously you can't do it for like 2,000 structures, here you can actually use write a short Python program, and you can download the data for 2,800 materials in one shot. Okay, so what you need to use the API is the API key. So for all of you, please go ahead after today's lecture to go and sign up for an account on the materials project and get your API key. You can also look at the documentation on this particular website over here, which is api.materialsproject.org/documents. Okay. Now, basically, an API maps. What an API is essentially it maps a URL to a resource. So let me give you an example. I'm not sure how many of you still use Dropbox, but if let's say you submit a GET request to api.dropbox.com and you ask for account info, basically what you will return is the information on your user account. Okay. Obviously, you will need to supply some authentication, like what's your username and password. But essentially, what the API allows you to do is to get such information in a programmatic manner, right? Now, what this API is used for is that I, as an external user, can now write a software code to interact with your Dropbox account. Okay, so that's where if you look at all the various plugins that make use of Dropbox, so things like or Google Drive, for example, right? So you can integrate Google Drive into one of your email clients, and all those users are the respective APIs of that software, right? So in a similar fashion, the Materials Project API is meant for the same purpose. Obviously, we are not foreseeing that there are a gazillion developers out there who wants to build software for Materials Project, but one of the primary users of the Materials Project API is to really get data for machine learning and data analysis. Okay. So I already showed you the materials project API example, but here I'm going to show you what is exactly returned by the materials project API. So if you submit a request to this URL, api.materialsproject.org, you go for summary, you say I want everything with the formula FE203. So you see that I actually colored all these parts of the URL. So this is the preamble, right? So this is basically the main part of the URL. This says this is the function I want to call. I want to get a summary document. I want to get it for everything with the formula FE203. And the fields that I want is things like the formation energy per atom. Okay? And what you will return is basically this what we call a JavaScript object notation, or JSON document. And this JSON document will contain exactly the information that you have requested for, and all the for everything in the materials project that has a formula of FE203. Okay? Now, the nice thing about this kind of response, JSON, is that because it is a very standardized format, in almost every single programming language out there, it doesn't matter what programming language you're talking about, whether it is Python, Java, or JavaScript, or C, you always have parsers that can automatically read in that data and give it to you in a format that you can actually do analysis on. Okay? You also see that there's some metadata that is attached to the response to you. This tells you that this was returned to you using the API version 0.48. There's a total of 26 documents that were returned, and there's a timestamp there. And all these are just useful information in case, let's say, 10 years down the road, you decide to rerun that same query, and you find that, oops, now instead of 26 documents, I have 100 documents. What exactly is different, right? And we potentially can track it down, what has changed in the intervening period, okay? What are the types of materials data, right? And this is not unique to materials data, obviously. This classification also applies to other forms of data. So typically data is categorized in three forms. One is qualitative data. Now, a qualitative data measurement is basically a nominal form of measurement. There is no ranking involved in that piece of data, right? So for example, when you say something is a metal or insulator, you are passing no judgment whether a metal or insulator is a better ranking, right? Obviously, in some applications, you will want metals. In other applications, you will want an insulator. But this is by and large not a ranking measurement, right? One step up from qualitative data is what we call ranked data, right? In ranked data, you are still measuring in terms of categories, right? So it is not a quantitative value, but rather a ranking. And in this case, you actually have passed judgment on whether there's an order to the sequence of categories, right? So for instance, an example that I can use is if I'm ranking a material based on its conductivity, I'm going to say that, well, this material doesn't conduct electricity at all. It is an insulator. This material conducts some electricity, at least in some situations. Then we call it a semiconductor. And of course, if this material conducts electricity freely, we call it an electrical conductor, right? Now, another example, which is non-material science, is of course things like Olympic medals. There is a gold, silver, and bronze. There is a very clear ranking between gold, silver, and bronze, okay? Now, the thing about ranked data, though, is that in such classifications, you usually do not have a distance between ranks, okay? So, in other words, for example, there's really no quantification of, for example, what's the difference between a gold medalist and a bronze and a silver medalist in terms of, say, for example, the time between them, okay? And this is one of the limitations of ranked data, right? Now, the last kind of data is really the kind of data that where machine learning techniques actually come into the most power, which is quantitative data. Now, when we talk about quantitative data, there's a well-defined interval or ratio measurement, okay? And there is actually a value that you measure. So things like, for example, when I talk about the melting point of a material, or the elastic constant of a material, or the electrical conductivity or ionic conductivity of a material, that is a quantitative measurement. And it is this kind of data that actually provides a lot of information for you to do arithmetic operations, okay? Now, in this course, you will learn about different kinds of machine learning techniques. There is the regression models, which primarily works with quantitative data. In other words, you are trying to predict a value. So you want to predict, for instance, that the melting point is 100 Kelvin, or you want to predict that the melting point is 300 Kelvin, for instance, okay? There is also another kind of machine learning model, which is called classifiers. Classifiers are used for the first two types of data, okay? So you are not actually trying to predict a value, but rather trying to classify whether something, that particular material is in one class or the other. So for example, you want to classify whether a material, you want to predict whether a material is a metal or insulator. That is called a classification task, okay? Now, so what is machine learning? So I'm sure that you have heard a lot about machine learning in the news. And basically, machine learning is this essentially a way in which you develop algorithms that automatically learn from the data. So it is very unlike how we used to build algorithms to make predictions, okay, previously, right? So not too long ago, the way that you actually build something that classifies whether something is a metal or insulator is that you will actually specify rules, okay? You will say, well, if this material contains a metal, but it contains only metals and it doesn't contain any of the more electronegative elements, then I'm probably going to classify it as a metal, okay? While if something actually has oxygen in it, the likelihood is that it is an oxide, which tends to be insulating, right? Now, in machine learning, basically, you don't actually define the rules, or rather the algorithm is going to learn the rules for you by you actually supplying the algorithm with all the data for it to basically infer the rules from the data, right? Now, when we talk about machine learning, there are many, many different types of machine learning, okay? So the biggest form of machine learning that that we are going to cover in this course is called supervised machine learning, which is what I just said, in which you basically give it data and you give it labeled data, and the algorithm that essentially learns how to make predictions, okay? So examples of where supervised machine learning is applied are things like, for example, image classification, or if you want to predict the quantitative value of a property of a material, all those things are supervised machine learning models. Now, there's also what is called unsupervised machine learning models, and we are also going to cover this, okay? And this kind of machine learning models also have their application. So in unsupervised learning, there is no label associated with the data. So in other words, all you are giving it is basically just a cluster of data points, and that algorithm that essentially learns what categories there are, or it learns how to separate out different types of categories within the data that you just gave it, okay? Now, you also use unsupervised learning for what is called dimensionality reduction. So what dimensionality reduction means is that, for example, you may start by saying, I'm going to try to predict the melting point from this 16 different features of a material, but how do you know that you actually need all 16 features, right? So maybe that 16 features is really not 16 features, but actually only 2 or 3 effective dimensions of features, and that's where your dimensionality reduction techniques actually come in, okay? Now, Obviously, machine learning has already affected your lives. Anyone carrying a cell phone today actually has machine learning algorithms on their cell phones. Of course, there are much more sophisticated applications of machine learning. So when we think about things like AlphaGo or AlphaZero, those are machine learning models that have defeated the world's best players in chess and Go just not too long ago. We know of many, many car companies that are developing self-driving cars. The key requirement for you to be able to for a machine to be able to self-drive a car is for it to be able to detect what is around it and then make decisions based on what it detects. And that again is a machine learning algorithm. Okay? And if you go to Netflix and you decide what to watch, and you see Netflix actually tells you, well, I'm going to recommend that this show might be interesting for you based on your watch history. Again, that is a machine learning algorithm. Okay, that's a form of reinforcement learning. Okay, if you tell it, for example, I like to watch The Godfather. Okay, then maybe you would like to watch Goodfellas as well, right? But maybe Avengers is not really for you if you are a Godfather fan, right? All right. Now, in material science, this is a very general workflow of how you would go about conducting machine learning for a particular problem. All right. There's this 5-step process that I usually like to think about to organize my thoughts. Okay. So the first step in any machine learning effort in material science is always you want to identify what is the problem or purpose or target of your machine learning project. All right. So here you really want to ask yourself questions like, well, is that problem even worth solving, right? Are you solving an important enough problem? Even if you are solving an important enough problem, is that target learnable, right? So there are many, many different material properties where we do not actually know enough about the problem to make any useful guesses as to how to go about applying a machine learning algorithm on them. Okay, so one example, for example, is superconductivity. Right? We do not actually have a unifying theory of superconductivity. If I ask you today, well, can you build a machine learning model that will predict the next superconductor? You will be hard pressed to do so because there is really very little you can go on in terms of how you predict a superconductor. Right? The other kind of question you may ask is the target ambiguous, right? So do you actually have a way of defining the target in a way that you can actually use it for decision making, right? And this first step is the most important, and it is also where all your knowledge and experience as a material scientist will come in, okay? There is no technical data science technique which will answer these particular questions for you, right? You have to be able to answer these questions for yourself. Now, let's say you already passed the stage, right? And you think that you actually have an interesting problem where machine learning may and may not actually help you make an impact, right? The next step you would go about is to collect data or to generate the data that you need to train your machine learning model, right? Now, the good news, as I've shown you in previous slides, is that first of all, there are a lot of databases out there, such as the Materials Project or OQMD or AFlow or whatever that you choose to use, that already contains a large data set for you to start with. All right. So there are also experimental databases as well. A lot of these are proprietary, so those are a bit harder to use. Okay. And also there are a lot of frameworks which can help you generate the data that you need, right? So my group specializes in things like high throughput computations. So we actually develop software that allows us to run first principle calculations over a large quantity of materials, okay? And we can generate a very large amount of data in a fairly reasonable amount of time if we are interested in that problem in the first place, okay? Now, after you actually have the data, the next step is to featureize your data. When we talk in machine learning, when we talk about featureization, what it simply means is that you need to have some way to describe your data, okay? So when we talk about describing the data, essentially it just means how do you create a vector that describes each material, right? There are many ways in which you can do it, but there are two broad categories of features that people use to define materials. The first kind is what we call elemental features or compositional-based features. What this simply means is that these are features that you derive directly from just the composition alone, right? So for instance, I am looking at iron oxide. The formula is Fe2O3. I know some properties of iron and oxygen, like the electronegativity of iron and the electronegativity of oxygen. Can I define my material using those electronegativity numbers? Okay, so those will be what we call elemental features or compositional-based features. Now, of course, composition is a very important part of a material. It is not the only part, right? And there are limitations with just purely using compositional features in your machine learning model. And one of the most major limitations that you will face is that composition doesn't describe structure, right? So for instance, diamond and graphite, exactly the same formula. It's basically C, right? But they are very, very different. One is a transparent and hard substance. The other one is an opaque, slippery substance, okay? So if you are, for example, building a machine learning model to predict the bulk modulus of materials, and some of them are polymorphs, like for example, carbon and graphite, just using compositional features alone, your machine learning model will never learn the difference between graphite and diamond, okay? So this is why the second set of features that people think about using are features that describe the structure of a material, right? And there are many, many different types of these kind of features. The key criteria always is that it must obey the symmetries of the system that you are working with, right? So for instance, if I take a molecule of methane and I rotate it by 180 degrees, that molecule should still have the same property, right? The properties of the molecule shouldn't change when I just rotate the molecule. So I need a way of describing the molecule that also obeys this kind of symmetry invariances, okay? Now, once you actually have your features, and here, this is basically, I would say, about 80 to 90% of the work in machine learning for material science out there is focused primarily on this step, okay? Now, this is actually not going to be the main step that you guys are going to worry about in this course. We are going to at least tell you what are the initial features you'll be using, at least for labs 1 and 2. You will actually be learning a lot about step number 4, which is how do you go about training your model, right? And because of the increase in popularity of machine learning models over the past few years, and there are a lot of software packages out there that already pre-built all the machine learning models for you. All you need to do is to basically give it the data to fit the models, okay? So things like scikit-learn and TensorFlow, especially scikit-learn, which will be the primary package that you will be using for this course. And, after training, of course, the last step is to use your model, right? And you will go ahead and apply it. And very frequently, more often than not, when you try applying it for the first time, you might be disappointed, or you may find that, well, it works too well for me to believe that it is true. And then you will go back and think about whether I should be generating new data and new features or new model, trying out new models. Okay, so there is sort of a feedback loop in which you will fine-tune your models as you go along. Okay. All right. So before we jump into machine learning, so remember that very first question that I wanted you to ask yourself. Well, is this a problem that we really should be using machine learning for, right? And this is by no means an exhaustive list, but at the very least, it is a list of the kinds of problems that I think is where machine learning is particularly useful in material science, okay? There are problems that are too many to compute. In other words, even though today we can do something like high throughput DFT calculations, you still cannot compute all of them, right? So that's one class of problems, okay? There are problems that are too big to compute, okay? So first principle calculations are notoriously expensive and poorly scaling. So I can easily calculate a material with up to 100 atoms. If you give me a material with 1,000 atoms, it's actually much harder for me to run DFT calculations on them, right? So this cell that you see here, this is a polycrystalline high entropy alloy that we simulated, and this contains 500,000 atoms, and you can't do DFT on 500,000 atoms, okay? Then there's the last kind of problem where it's actually quite interesting, which is in problems that today we really do not have a good way or good understanding of how to perform a particular mapping, right? So this is actually very similar to how machine learning is actually used in other fields like image recognition or medical imaging, right? Well, for example, one of the ways that you would try to understand what is inside a material is that, for example, you may do an X-ray exhaustion spectroscopy on it or X-ray diffraction experiment on it, and you measure something like this, right, which is a spectra, right? And frequently, what you want to get from this spectra is some information about the material, right? Is it nickel, iron, or cobalt? Whether that nickel, iron, or cobalt is sitting in a tetrahedral or octahedral, or does it contain some defects? Okay, so these are all the kinds of questions you will want to try to answer from your spectra, right? And frequently today, the way that you will answer this question is you take this spectra, you go and measure a few other spectra of reference materials. Okay, so things like you already know this is Fe2O3. So you're going to compare the Fe2O3 spectra with this and check whether this looks like Fe2O3 or not, right? So that's, again, a very human-intensive effort and also is not particularly efficient, right? So one of the ways that machine learning can help in this regard is really to automate this process, right? Can we actually just have a machine try to learn, well, if I look at this spectra, I can actually interpret the peaks, positions, or the features of the spectra and directly say, well, this looks like iron in an octahedral site, for example, okay? And again, this is, of course, still a very active area of research, and people are developing new models every day, okay? Now, so let me talk about the first class of problems, which is the ones that are too big to compute. This is by far the area where I spend the most of my time on, especially with regards to machine learning for material science. So this is a data history of the materials project, right? So what you see here is basically the number of crystals in the materials project with computed energies, band structures, elastic tensors, and phonons and XAS spectra over the course of the lifespan of the materials project so far, right? So this chart was made right before the pandemic. That was 2019. So I only have data up to then, but by and large, the numbers haven't changed all that much in the past 2-3 years, okay? So what you will notice immediately is that, first of all, on our y-axis, this is a log axis, okay? So these are in powers of 10. And what you will notice is that if you look at the number of structures, we have sort of stagnated at about the same number of structures over the past few years, okay? We have been at around 130, 140,000 structures for that amount of time. And correspondingly, we also have that amount of energies, okay? Now, if you look at other properties, so things like the elastic tensors or the phonons, the data set is actually at least 1 order of magnitude or 2 orders of magnitude smaller, okay? And the reason for that is very simple. It is because these properties are much harder to calculate using your standard first principles techniques, okay? And so there's a limited number we can do, and we prioritize certain types of crystal structures and went ahead and calculated them, all right? Now, so why do we actually need machine learning? The problem with this is, though, is that, oops, why is this here? The problem is, of course, that materials design is actually a combinatorial problem, right? So whenever we think about, well, what kind of material can potentially exist that may actually work for my application, there is usually a huge space of potential materials that you want to look at, right? So for example, you want to design a new alloy. Let's say you want to develop a new ceramic, okay? And you are interested in this class of ceramics called high entropy perovskites. And if you just think about a very simple perovskite cell where you consider two A atoms and two types of A atoms and two types of B atoms, and you just give it 10 different species to try to figure out what are potentially the total number of materials out there, we are already talking about 10 to the power of 7 materials, okay? 10 to the power of 7 is orders of magnitude larger than anything that we have computed before, and there's no way we can use DFT to access this space in a very timely fashion, okay? So this is really where machine learning comes in, okay? And the idea here really is that we want to use machine learning techniques on the data we already have, and then try to make predictions about materials that potentially are hypothetically are out there, and using that to guide our decisions on what new compositions, what new structures we should be exploring for our application, okay? And again, here the good news is that we have crossed the threshold of having enough data for some reasonable machine learning, right? So we don't have the millions or billions of data points that, say, someone working in the social sciences would have, but we do have enough data for useful machine learning models to be built, okay? What you actually want is to build surrogate models that can instantly give you a prediction of what that material property is from either the composition or the structure, right? So in machine learning terms, so this is formal machine learning terminology, so you should remember that. The property, or rather the thing that you want to predict, so things like, for example, the energies, like the formation energy, or the what we call the energy above Hall, or the reaction energies, or binding energies, or whatever you want to predict, or the electronic properties like band gaps or DOS, the mechanical properties like your bulk modulus, shear modulus, or the application-based properties like ionic conductivity, or band gap, or solar efficiency. These are called the targets, okay? The target is basically the thing you want to predict. Now, composition and structure are called the descriptors or features, right? So remember, this is usually the step where people spend the most time in developing machine learning models for material science. So some examples of compositional features, things like stoichiometric attributes, so things related to the composition, things like what's the number and ratio of elements, what are some of the elemental properties like the mean or the range or the minimum and maximum of things like the atomic number, electronegativity, the row and group number, atomic radii, and number of valence electrons, so on and so forth, okay? So people have tried all these different types of features, okay? Structural features, as I mentioned, you do need to obey the symmetry of the systems that you want to work with. So people can use things like symmetry basis functions to describe the structure. They can also use things like the lattice parameters, the atomic coordinates after you transform them in some form, or maybe things like the connectivity and bonding between atoms to describe the structure, okay? So these are just a few works. It's not important that you focus. It's not important for you to focus too much on the actual applications here, but I just want to show you that this is basically a very active area of research. So there is this work by Meredith et al. Back in 2014, where you can see that they actually use this huge list of features to basically develop machine learning models to predict various properties, okay? Subsequently, if you are working with something simple, like, for example, just the perovskite, where the structure is already fixed to a certain types of form, a compositional-based featureization approach can work well, and you can then, so people have applied that together with a convolution neural network to basically predict various properties as well, okay? In terms of structural features, things like, for example, people have used materials fragments. So for example, what's the local environment around each of the atoms to describe a material. They can the state of the art are what are called graph neural networks. In other words, you use a graph to describe a material, right? So graphs are actually a very natural representation for either molecules or crystals. You can think of the nodes in the graph as basically your atoms, and the edges in the graph as basically the bonds between the atoms. And that gives you a very natural representation, and it also obeys all the symmetry constraints that you would have for your crystal, okay? There are also things like smooth overlap of atomic positions. Again, these are based on the atomic density around each atom. And this particular type of featureization approach is very popular for developing machine learning interatomic potentials, okay? So an example of a graph-based representation, this is a graph neural network-based approach that came out of my group, which is called materials graph networks, or what we call MAGNET. So basically, the way that this works is that you represent, for example, the bonds and atoms as a vector of numbers, and you essentially just pass information from one part of the graph to another, right? So this kind of machine learning models are also called message passing neural networks, okay? You essentially have steps in which you say, I'm going to update the information on this bond using the vector information from the atoms that are bonded to it, and then I have a new bond vector, and then I update the atoms, and I update the global state, and I just keep repeating this process. I stack a number of these layers, and basically what I get is a machine learning model, okay? Now, this kind of machine learning model is, I would say, among the best performing so far in terms of being able to predict material properties. So up here you see basically graph network models that have been developed for various molecular properties of the QM9 data set. You can see that we can actually predict things like the internal energy or Gibbs free energy or HOMO or LUMO levels of a molecule to a very high degree of accuracy, right? In essence, all these predictions are well within what the chemist considers chemical accuracy. In other words, an accuracy that's sufficient for you to really use that information, use that prediction in a practical way, okay? Similarly, you can also apply graph neural networks to things like crystal properties. So things like the formation energies, we can predict them to within 28 milli-electron volt per atom. Again, this is a good enough number for you to, even before you go into experiments to try to make a material, this is a number that is good enough for you to say, well, am I likely to be able to synthesize that material or not? Or is that material so high in energy that trying to synthesize it experimentally is hopeless, okay? So it is this kind, so this kind of accuracy is really good enough for that purpose. Things like band gaps, the state of the art is around 0.2 to 0.33 electron volt. Again, pretty good enough for you to distinguish between metals and insulators and semiconductors for sure. Is it good enough for you to design a solar cell? Maybe, maybe not. You may want to target the band gap a little bit more, but at the very least, you know what materials to exclude, right? There are certain materials where the band gap is not going to be even close to what you need for a solar cell, right? Bow and shear modulus, and I'm going to talk about this later, and things like classification of whether something is a metal or insulator, okay? Now, the second type of problem that machine learning models are particularly useful for is to address the scale challenge in material science, right? So this is essentially the problems where it is too big to compute. So the first principle methods that I talked about, they are very accurate, right? They are so accurate that today it's very common for any paper to actually have some first principle calculations to essentially just show that the predictions from first principles is actually in line with what experiments observe, right? But the real world is much more complex than that, right? So in all experiments, you seldom get something like a nice bulk crystal with a few atoms that you can actually work with, right? More often than not, you have very messy systems, things with microstructure, you have grain boundaries in them, you have defects in them, you have surfaces in them, you have nanostructures, okay? And all these things require you to be able to model the system at much larger length scales, okay? And this is where traditionally things like empirical potentials actually come in, right? So empirical potentials are essentially models that you build to describe the potential energy surface of a system, in other words, the energy and forces in the system. And traditionally, you build such models based on some rigid functional form of the pair distance between atoms or the angles between atoms, okay? Now, the critical challenge is really, can we actually build models that have somewhat close to the accuracy of first principle methods, but yet you can actually use them to simulate much larger length scale systems, okay? And this is really where machine learning has blossomed, okay? I would say by far, this is the most successful application of machine learning in material science today, okay? It is not in predicting properties. Predicting properties is something that everyone is interested in doing. There are a few successes, but they are not like, it is not so successful that you would run out there and say, I mean, machine learning is the next big thing in material science. But machine learning as a means of addressing the scale challenge, this is a definite success story, okay? So today, it is very standard that you can use a set of local environment descriptors. So in other words, so for example, things like the angles or distances between atoms, you describe them using various basis functions. And you then apply a machine learning model to describe the energies and forces on each atom as a function of that local environment descriptor. And these machine learning potentials are now so accurate and so overwhelmingly more accurate than the previous empirical potentials that it is almost a standard process that you can now develop machine learning potentials for a problem that you're interested in, okay? Now, the key thing about machine learning intelligent potentials is not really just about the accuracy, okay? So a lot of people think machine learning intelligent potentials is like, wow, they can get 1 MeV per atom. That's so much better than the 20 MeV per atom I'm getting with EAM. Well, that is just one of the reasons, right? The main reason why you care about machine learning intelligent potentials is that it is automatable, right? Today, I can actually pass any new student a recipe for creating a machine learning intelligent potential, and he can go about and follow that recipe, and he probably can get it for get a potential fitted for any system he chooses to look at, okay? And that was not the case in the past, right? So in the past, let's say someone wants to fit a new EAM potential for, say, BCC Morley. That is usually one PhD project, okay? He takes 5 years, and you publish that paper and you're done, right? So nowadays machine learning potentials are so easy to do. My students can fit the potential within a day or two, okay? So it is completely a different kind of world here. So just to show you what kind of things you can do with machine learning intelligent potentials, you can simulate things like, for example, a solid liquid equilibrium cell. So here, really what we are trying to do is to reproduce the nickel-Morley phase diagram. And here I show you basically things like the EAM results, the CalFET results which are fitted to experiments, so those are definitely accurate. And this is basically what a machine learning intelligent potential gets. And what you can see is that the agreement of the machine learning intelligent potential with experiments is extremely high, right? Compared to something like traditional EAM, which is completely inaccurate, right? And with this kind of accuracy, you can start doing interesting things. Like, well, one of the key relationships, if you are a mechanical engineer, is what is called a Hall-Patch relationship, right? When you actually change the grain size of a material, that actually affects the yield strength of your material, right? And there's a well-defined relationship between your grain size and your yield stress, and now we can actually use simulations to verify that relationship, okay? Now, to actually create polycrystalline materials with grain sizes of things like 11 nanometers or 4 nanometers, you really need very big cells of up to about 500,000 atoms, 1 million atoms, okay? So you can't do that using DFT, right? All right, so and finally, the last type of problem that we are interested in are basically the problems where we want to model very complex relationships. One of the big successors of machine learning, or at least deep learning, which is neural networks, is in image recognition, right? So this just shows you how much progress has been made in the field of image recognition over the past few years, right? So back not too long ago, just about 10 years ago, the state-of-the-art machine learning model for image recognition, you basically get an error rate of about 28%. In other words, you are accurate only about 70% of the time, okay, for image recognition, right? Today, with the state-of-the-art deep learning models, things like convolutional neural networks-based models or recurrent neural networks-based, convolutional neural networks-based models and other kinds of sophisticated models, you can actually get accuracy of easily 97, 98%, okay? So if you are wondering how Facebooks know how to label all your friends in your photos, this is basically how this was done, okay? And this is essentially, this is the quintessential demo problem for machine learning in the past 10 years, okay? So this is where a lot of the competitions are held. There's this big data set called the ImageNet data set, and people have been using that data set to compete, see who can come up with the best models for that particular problem, okay? So in material science, obviously, we have similar problems. Like I said, we want to know, for example, this spectrum, what kind of coordination environment does this spectrum represent? And so we have actually played around with many different types of models. So you will learn about all these models in the lectures. And we can essentially get up to an 80% accuracy in classifying whether something is, say, in a tetrahedral or octahedral environment with these machine learning models, okay? And this is, of course, just a proof of concept. There are still a lot of problems out there that people are still trying to apply machine learning problems for this kind of interpretation, okay? So there's an example, for example, that XRD classification. So this is, of course, one of the big problems that everyone wants to solve. So for example, today, let's say, by some chance, you went to the lab, your PhD advisor has said, well, try throwing all these materials together and heat it up to 1000 K, see what happens, and you suddenly see a new phase of material, and it didn't match any of the existing XRD patterns. So you are very happy. This is probably a novel material, and you want to figure out where the atoms are, right? This is where XRD comes in, and you want trying to figure out where the atoms are from an XRD image is not, XRD spectrum is not a trivial problem, okay? All right.